Good afternoon. Welcome to the Peck Lecture. It's my great privilege to introduce this year's speaker, Dr. Lelio Mejia. He is a registered civil and geotechnical engineer with over 40 years of professional experience. He is a senior principal with Geosyntec Consultants in Oakland, California, and leads the firm's West Region Dams and Levees practice. His main fields of expertise include dam engineering and soil liquefaction, soil structure interaction, and soil improvement. He's the chair of the Earthquakes Committee of the United States Society of Dams and vice chair of the Committee on Seismic Aspects of Dam Design of the International Commission on Large Dams. He recently served on the committee of the state-of-the-art and practice and earthquake-induced soil liquefaction assessment of the National Research Council and was a secretarial appointee to the Advisory Commission on Structural Safety of Department of Veteran Affairs Facilities. He has been an invited keynote speaker at multiple national and international conferences as a member of the National Academy of Engineering. Please help me in welcoming Lelio.
Thank you for the kind introduction, Jim. I am honored and very pleased to present this year's Ralph Peck Lecture, which I have titled Earthquake Cracking of Embankment Dams. First, I would like to thank the ASCE Geo-Institute and its awards committee for awarding me the Peck Medal, and Professor Ed Idris for nominating me for the award. Many teachers, colleagues, and professional friends have helped me throughout my career, and it would take too long to thank them all individually. However, I would like to especially acknowledge some of my mentors who guided me and had a profound influence on my career, namely Professor Harry Seed, Professor Idris, and Mr. John Bishop. I would also like to especially thank some of my professional colleagues with whom I've have collaborated closely over the years. Professor Ross Boulanger, Dr. Ethan Dawson, and Mr. Murray Gillen, both of whom actually contributed significantly to the work that I will present here. Like for many of us, Ralph Peck had a pronounced influence on my education. I was exposed early in my undergraduate studies to his textbooks and later on to his writings, several of them about dams. I only met Professor Peck once at a conference where, after I had presented a technical paper, he approached me and we spoke for a few minutes, and he complimented me on my presentation. That, of course, made me feel very good, and it made me internalize what I already knew, that he was not only a giant of our profession, but a very kind and generous person. In today's presentation, I would like to provide an overview of the effects of earthquakes on embankment dams, discuss the potential for embankment dam failure by cracking, review some of the basic concepts from the mechanics of cracking in soils, discuss the analysis of dam cracking in practice, present two case histories of embankment dam cracking, and finish with some conclusions. Past experience has shown that earthquakes can affect embankment dams in multiple ways. The potential effects of earthquakes on those dams include slope failure of the embankment, sliding of the embankment through the foundation, embankment deformation and settlement, embankment cracking, shear of the embankment and its foundation by surface fault rupture, differential tectonic displacement of the reservoir and of the dam foundation, reservoir rim landslides, which could lead to overtopping of the dam, and failure of the spillway or outlet works. Previous observations have shown that embankment dam cracking is one of the most common and hazardous effects of earthquakes on embankment dams. Cracking is usually observed at the crest of dams and along the upstream slope and the downstream slopes, and can take various orientations and shapes. However, past observations have also shown us that earthquake-induced cracks are commonly oriented in longitudinal and transverse directions relative to the dam axis. As pointed out by Sherrard in 1973, earthquake-induced cracks are frequently similar in pattern to cracks due to static loading. Cracks are typically near vertical because of the sustained stress field imposed by gravity. However, they can also take non-vertical orientations due to arching, depending on soil strength, geometric constraints, and stiffness discontinuities. It is also important to note that embankment dam cracking can also result from desiccation or hydraulic fracturing in the absence of general embankment deformation. The mechanisms of dam deformation and cracking induced by earthquakes are generally associated with transverse spreading of the embankment and settlement of the shells, which lead to tensile strains normal to the dam axis, resulting in longitudinal cracking. Strong earthquake shaking and dam deformations along the longitudinal axis of the dam, as well as settlement, can lead to transverse cracks, particularly near steep abutments or above irregularities in the foundation profile of the dam. Our experience tells us that earthquake cracking can lead to dam failure and breaching in multiple ways. And earthquake-induced cracking is an early step in various potential failure modes in embankment dams. For example, cracking can lead to increased seepage and leakage, which in turn can lead to internal soil erosion and piping failure of the dam. Or it can lead to embankment saturation and instability, or both. Cracks oriented transverse to the dam axis, in which allow concentrated flows through the embankment, are particularly dangerous. The mode of failure of embankment dams by cracking and piping can be visualized by considering a zoned embankment dam with pervious shells, a clay core, and a chimney filter and drainage blanket. Let's assume that an earthquake occurs and cracks the core crosswise below the reservoir level. The crack provides a conduit for concentrated leakage across the core. Under these conditions, we have two possible outcomes. First, the filter is effective and stanches the leakage and prevents the progression of internal erosion, or the filter is ineffective and allows continuing erosion of the core to occur. In the latter case, potentially this can lead to internal erosion progressing to a piping failure. It is important to remember that cracking can occur at depth. In fact, at significant depths, as I will show later. It is also quite clear that filters and drains are critical elements to the safety of embankment dams, in that filter design requires careful consideration. And evaluation of this type of PFM, potential failure mode, requires reliable assessment of the potential for, in the location and extent of cracking. To better understand the potential for cracking in embankment dams, it is useful to review some of the basic concepts about the mechanics of cracking in soils. Firstly, earthquake-induced cracks in dams generally result from permanent embankment deformation. This is because seismic deformations may cause tensile stresses in the embankment materials. Cracks are initiated when those tensile stresses exceed the tensile strength of soils and commonly nucleate or originate at flaws in the material. Once a crack is formed, it induces a non-uniform distribution of stress around the crack, such that the crack, once initiated, the cracking in soils continues to propagate until the driving stresses conditions change or the capacity of the soil to support an open crack is exceeded. Failure of soils, I should say, tensile failure of soils is typically quite brittle. And this is because cracks propagate by fracturing as opposed to yielding off the soil. Where cracking can be expected to occur when and where the tensile stress exceeds the tensile strength of the soil. When the tensile stress reaches the tensile strength, the material completely loses its ability to carry tensile stress. Although the process of cracking is very complex and is controlled by the principles of fracture mechanics, cracking of intact soils may be approximated as a strength of materials problem. These concepts provide a basis for the analysis of cracking in practice. That analysis generally consists of identifying zones of extension where tensile stress exceeds the tensile strength of the soils. It is important to note that transient earthquake stresses and deformations may open and close cracks temporarily. However, cracks that remain open after the earthquake are associated with permanent dam deformation. Therefore, analysis methods for continuous media are generally satisfactory in practice, provided they can simulate permanent dam deformation. This means that nonlinear analysis methods capable of simulating earthquake-induced dam deformations, permanent deformations, I should say, are required to estimate potential cracking. Because the tensile strength of soils in the laboratory and in the field plays an important role in cracking, it is useful to understand the factors that affect such strength. These include soil type, the loading type and loading rate, which basically is dependent on the type of test or condition in the field, the water content at the time of loading, and the placement conditions of the soil, including its density and water content. In these tests, for example, you can see that the tensile strength of soils varies from relatively low values of about 15 kPa to moderate strength values of maybe 75 kPa, and peaks at around at a water content near just dry of the optimum water content. The strength that matters for analysis, however, is the field strength. And in this regard, it is important to keep in mind that because cracks nucleate at flaws in the material, in the soil, the tensile strength of soils depends on specimen size. Laboratory testing has shown that the tensile strength of soils decreases inversely proportionally to the volume of the stressed soil. And this is expressed by this equation where the tensile strength is basically a direct function of the volume of a specimen subjected to at least 95% of the maximum tensile stress. Because the volumes involved in the field are very large, it follows that the field tensile strength of embankment dam materials is generally 1/10 to 1/30 of the strength in the laboratory and is typically very low. Therefore, for dams, it is quite common to assume a zero tension cutoff in the analysis. And this is important because overestimating the tensile strength of soils leads to underestimating the potential and the extent of cracking in the field. In addition, it is important to consider that crack widths are determined by the magnitude and spatial extent of tensile strains and are correlated to the depth of cracking. The depth of cracking, however, is limited by soil cohesion or apparent cohesion. And generally, the maximum depth of cracking can be obtained from this expression, where C is the cohesion of the soil and phi is the friction angle. From this expression, it follows readily that coarse, cohesionless soils are unable to support open cracks. Therefore, in embankment dams, zones of these materials will not crack. It is also important to note that fine-grained, partially saturated, cohesionless soils can temporarily support open cracks and hold a roof. With this background in mind, let's examine two case histories of embankment dam cracking that illustrate the potential for cracking during construction and reservoir filling and earthquake shaking, and also the ability of current methods of analysis to simulate potential cracking. The first case history corresponds to the Matahina Dam in the North Island of New Zealand. This case history will examine cracking during construction and reservoir filling, and then during a large earthquake in 1987. The second corresponds to Lelio Dam in California. In this case, we'll examine the response of the dam to strong shaking during a major earthquake and the ability of numerical analysis of seismic response and observed cracking to simulate those effects in dams. Matahina Dam is a rock-filled dam with an inclined earth core and a height of 82 meters, a crest length of 420 meters, a freeboard of a minimum operating freeboard of 3 meters below the crest elevation. It retains a reservoir of 55 million cubic meters, and the population at risk downstream of the dam exceeds 100 people. This image on the right side here is a view of the dam prior to retrofit of the structure in 1997. And this is the corresponding maximum dam section. The outlet works and spillway are sited on a rock spur that protrudes into the river valley and also forms the left abutment of the dam. The dam and foundation materials include a central core of gravelly, sandy clay silt to silty clay, which was densely compacted dry of optimum. The core is flanked by upstream and downstream inner transitions, which are densely compacted gravelly sandy silt to silty sand. Outer transitions of compacted sandy gravel with cobbles separate the inner transitions from the rock-filled shells. And those shells consist of compacted, quarried, hard ignimbrite rock. Now, the shells are founded on dense, coarse alluvium, and the embankment core and the alluvium are founded on tertiary sedimentary rock, while the abutments are made of hard ignimbrite rock. Hard ignimbrite rock also underlies the downstream toe of the dam. Please take note of the steep and stepped nature of both abutments. And also note that seepage through the dam and the foundation is collected by a central drain and weir referred to as the main drain weir, which discharges into the original stream channel downstream of the dam. The vulnerability of the dam to internal erosion can be evaluated by examining the particle size distributions of the dam materials and other engineering characteristics. Such examination indicates that the core and inner transition materials first are readily erodible, two are not filter compatible, they basically have the same gradation, and in addition are very stiff and have a high cohesive strength, and therefore are able to crack and hold a roof. The outer transition materials are not filter compatible with the inner transition in the core, and their gradation is also susceptible to segregation during placement. In addition, the rock fill in the shells is very coarse. So all these conditions basically indicate a clear vulnerability to internal erosion within the embankment. The dam was constructed between 1965 and 1966. As the embankment was raised, settlements of the fill were measured using settlement cells installed at various elevations within the fill. The measurements indicated first up to about 0.2 meters of settlement at the foundation contact, up to about 0.8 meters of settlement within the rockfill shells at around mid-height or so, up to about 0.5 meters of settlement in the inner transition near the dam mid-height, and up to 0.3 meters in the inner transition at a depth of 20 meters below the crest. And that is an important number to remember, the 0.3 meters. Interestingly, as the embankment reached a large height, vertical cracks were observed at the contact between the fill and the right abutment. The builders and designers drilled boreholes to investigate and repair the damage into the core, and those boreholes were subsequently grouted. The dam experienced a serious incident of internal erosion and piping during first filling of the reservoir in 1967. Initial reservoir filling began in December of 1966, and the reservoir rose quite quickly to about elevation 64, where it was held for 2 weeks. As the flows at the main drain weir increased gradually with the increasing reservoir level and stabilized at about 70 liters per second when the lake was held at 64 meters. And that corresponds approximately to about 2.5 cubic feet per second. A relatively large flow, but it was not unexpected by the designers. After 2 weeks, the lake was allowed to continue to rise. And when it reached 71 meters, the main drain flows increased suddenly to 560 liters per second, which corresponds to about 20 cubic feet per second. And worse, they became cloudy. Fortunately, after a few hours, the flows decreased and subsequently cleared, and they stabilized at about 250 liters per second, while the reservoir continued to rise to the maximum storage level of elevation 76. 2 weeks later, though, a 3-meter deep crater appeared at the crest, just downstream of the core, near the right abutment. The lake was immediately lowered back to elevation 64, and an exploratory pit was excavated at the crater location. The surface crater was found to be the top of an erosion chimney that extended to a concrete bench on the right abutment at elevation 67.4, 12 meters below the crest. Within the exploratory pit, 2-inch wide cracks were observed in the exposed faces of the core in the downstream inner transition. Actually, to depths of about 15 meters or so. In addition, traces of upstream inner transition material were seen in cracks in the core. And grout was observed in cracks within the downstream inner transition. It is quite likely that that grout was injected during the core repairs at the time of construction, but it's also possible that it flowed into the inner transition during installation of the abutment grout curtain. It was concluded at the time that about 100 cubic meters of downstream inner and outer transition materials had eroded through a rock-filled void at the abutment contact that was seen beginning from the exploratory pit. Years later, investigations revealed that differential settlements had led to cracking of the core and the inner transition. Cracks to a depth of about 25 meters had allowed concentrated leaks. And because of the lack of filter compatibility, those leaks had led to internal erosion of the core and inner transition into the outer transition. It appeared, though, that migration of the upstream inner transition material into the cracks in the core partly stanched the leakage. And interestingly, that condition withstood hydraulic heads of about 10 meters, while the reservoir rose temporarily to elevation 76 before it was lowered back to elevation 64. The core was repaired with a 0.6 meter thick patch of plastic concrete backed by granular filter material, as shown here on this cross section of the dam. Observation wells within in the backfill of the exploratory pit and the main drain flows indicated satisfactory performance of the repair for the next 20 years. On March 2nd of 1987, the Edgecumbe earthquake shook the region. It was a moment magnitude 6.5 earthquake with a normal faulting mechanism and a focal depth of 12 kilometers. The earthquake was located within New Zealand's North Island Whakatane Graben, which is part of this central volcanic region. And the main surface fault rupture came to within 11 kilometers of the dam and produced strong ground motions, which were recorded at 5 accelerographs at the dam. The peak accelerations recorded by the instruments on the main section of the dam are shown in this table, where it can be seen that the peak ground accelerations in the transverse direction at the base were on the order of 0.24 G, while at the crest were about 0.35 G, which is quite strong motion. The earthquake caused relatively small settlements of the crest, up to about 4 centimeters. In addition, the downstream slope vertical and horizontal displacements were less than about 10 centimeters and 25 centimeters respectively, and they decreased gradually down the slope. The upstream rock fill settled about 0.8 meters near the crest. At the same time, the core and foundation piezometers showed no significant changes from normal levels. However, flows at the main drain weir increased slightly and became turbid initially, but they decreased soon after. The reservoir was drawn down 2.5 meters as a precaution, and investigations were undertaken to evaluate the damage. The earthquake caused cracks at both abutments, and the cracks were several meters long, but just a few centimeters wide. In addition, a wide crack opened on the upstream edge of the crest as a result of settlement of the rockfill. There was slight spreading of the crest. Minor toppling of some rock was observed on the downstream slope. There was a small slip of fill at the right abutment. Flows through the rock spur on the left abutment increased substantially and became turbid temporarily. The investigations disclosed additional features. However, I would like you to note this puddle on the dam crest near the left abutment, which actually predated the earthquake by several years. 2 weeks after the earthquake, a 5-meter diameter erosion cavity was detected by probing upstream of the core at the right abutment. Because the main drain flows had not changed significantly, it was thought that the cavity was probably associated with the 1967 incident. 6 months after, however, drill holes found cracks in the core at the left abutment. Interestingly, the flows at the main drain seemed unaffected. However, 3 months after, an erosion cavity appeared on the crest. The reservoir was immediately drawn down in steps, and the decision was made to undertake repairs to the dam. While the reservoir was being drawn down, fluctuations in the piezometers within the core indicated continuing internal erosion in the core. And these are the types of fluctuations that were observed in the piezometers. It was also concluded that the former puddle was evidence of a prior episode of internal erosion. However, because the main drain flows in the piezometer levels, and actually the conditions at the crest had remained steady for many years, it was concluded that that episode had ceased well before the earthquake. However, that meant that the earthquake appeared to have disturbed a metastable stanch condition within the core and had reactivated internal erosion. The dam repairs consisted of reconstructing both abutments to depths of about 30 and 35 meters, very large depths. And the repair excavations revealed a number of important features about both incidents. First, they showed differential settlement in shears of up to 200 millimeters at steps in the abutments. In addition, open and incipient cracks to depths of 25 meters and over 35 meters respectively were seen in the excavations. Visual evidence was also observed of migration of the upstream inner transition into the core cracks, and there was visual evidence of migration of the core and downstream inner transition materials into the outer transition in the rockfill. In 1997, the dam was retrofitted for foundation fault rupture. However, that is another case history. Let's turn our attention now to Lenihan Dam, which was previously known as Lexington Dam. The dam is a zone earthfill embankment with a wide central core, a height of 208 feet, a crest length of 810 feet, and a freeboard of 70 feet above the maximum storage level. The dam retains a reservoir with a storage of about 20,000 acre feet, and the population at risk is well in excess of 1,000 people. Note the level of the reservoir in October of 1989 at the time of the Loma Prieta earthquake. The dam and foundation materials include an upstream shell of dense gravelly clay sands. These are materials that have about 15 to 35% gravel and maybe 20 to 50% sands and fines, and are quite dense in the materials in the upper 80 feet of the core, referred to as the upper core, are very similar, also dense gravelly clay sands. On the other hand, the core materials below 80 feet are a stiff, medium to high plasticity clay with actual plasticity indices in the range of 40 to 45%. The downstream shell consists of dense clay, sandy gravel. I also want you to note this zone, which corresponds to the internal drainage system within the dam. The foundation, it consists of Cretaceous sandstone and shale of the Franciscan Formation. The dam was constructed between 1952 and 1953 and has performed well since. That's partly because the materials were densely compacted and were placed in 4-inch thick lifts and compacted to over 95% of the maximum laboratory compaction density in accordance with the 19,500 foot-pound energy standard. From construction to October of 1989, before the Loma Prieta earthquake, the crest settled a maximum of about 1.9 feet, which is slightly less than 1% of the structural height of the dam. The dam underwent small to moderate shaking in earthquakes of approximate magnitude 5 on June 27, 1988, and in August of 1989, with less than 3/4 of an inch of settlement and no reported cracks. The earthquake motions during the August 89 earthquake recorded at the left abutment on rock at peak accelerations less than 0.1 G, and on the embankment at peak accelerations slightly greater than about 0.1 G. On October 17th, 1989, the Loma Prieta earthquake shook a large region of Northern California. This was a moment magnitude 6.9 earthquake generated by an approximately 40-kilometer long rupture on the San Andreas Fault, dipping about 70 degrees to the southwest. The rupture came to within 3 kilometers of the dam and produced strong shaking at the dam site, which was recorded by 3 accelerographs. One of the accelerographs was located on rock near the spillway entrance on the left abutment, and is referred to as the left abutment instrument. A second accelerodgraph was located on the embankment crest near the maximum dam section, and that one is referred to as the right crest instrument, and a third instrument in between referred to as the left crest instrument. The peak ground accelerations recorded at the site during the earthquake are shown in this table. And you can see that the peak ground accelerations transverse to the dam axis, basically this component here, on rock and at the maximum section were on the order of 0.45 G, which is very strong motion. The earthquake, as I said earlier, the reservoir was 117 feet below the crest at the time of the earthquake because of a prolonged period of drought. The crest settlements resulting from the earthquake were up to about 10 inches, 25 centimeters or so. While the crest transverse horizontal displacements were up to about 3 inches. Note that those transverse displacements correspond to slight rotation of the crest around the third point or so. In addition, after the earthquake, over the following 8 months, the survey monuments on the crest recorded about 1.5 inches of settlement. And I would like you to remember that the crest vertical and horizontal displacements had a similar pattern to the dam's long-term displacements. Piezometer levels within the embankment were measured with at several locations in piezometers and observation wells. During the earthquake, the piezometers in the piezometric levels in the core and the upstream shell rose 5 to 8 feet and decreased slightly over several months after. 6 weeks after the earthquake, a wet area appeared on the downstream slope and lasted for a few months. A downstream observation well rose up to 33 feet over roughly the same period. It is quite possible that that rise in levels of that observation well resulted from redistribution of excess pore water pressures that may have been generated within the dam's internal drainage system. As shown by a Stockwell transform of the recorded right crest transverse motions, the dam fundamental period of vibration for low intensity motion was elongated by about 20% by the earthquake. In addition, the earthquake resulted in transverse and longitudinal cracks to depths of up to 8 feet, and the cracks were generally less than about 2 inches wide at the surface. They were surveyed within days of the earthquake and were seen to correspond to transverse cracks along both abutments, as well as localized longitudinal cracks on the upstream slope and on the downstream slope. The rotation of the crest shown by the displacements of the surface monuments appears to have been controlled by the shape of the foundation rock contours. The wet area that appeared on the downstream slope directly overlaid the downstream edge of the core, and in fact, the overlaid the bottom of the drainage system within the dam. All of these observations, together with the recorded ground motions, make this case history an excellent case for analysis of the potential for embankment dam cracking. The approach used for the analysis of the dam consisted of using the motions recorded at the left abutment as input to a numerical model of the dam. The model was then used to evaluate how it predicted observed dam response in terms of several parameters, including the motions recorded at the right and crest stations, the crest settlements and transverse displacements, and the location and extent of dam cracking. This is a view of the model. It was a finite difference, three-dimensional, nonlinear total stress model. Two soil constitutive models were used, the Moore-Coulomb model and a parallel I1 model implemented by Dr. Dawson, both with a zero tension cutoff to represent the tensile strength of the embankment materials. Free field boundaries were used on the model sides, and a compliant boundary was used at the base to simulate the semi-infinite extent of the foundation bedrock. The left abutment motions were deconvolved separately using a horizontally layered model in one-dimensional methods, and were then input at the base of the three-dimensional model to drive the analysis. As expected, the three-dimensional model reproduced the recorded motions at the abutment quite closely, and this confirmed that the seismic response of the embankment had not affected the left abutment motions. Extensive data had been collected on the properties of the embankment and foundation materials and was used in the analyses. The maximum shear modulus of the materials was formulated from the measured shear wave velocities using this well-known expression in the parameters that are shown on this table. The strain hardening function for the I1 model was described by the modulus reduction relationship for each material. And plastic yield for both the Moore Coulomb model and the I1 model was defined by the soil shear strength obtained from the laboratory tests. The undrained shear strength was used for all materials, defined as a function of the consolidation effective stress, and the foundation rock was assumed to be elastic. I am only going to show the results for the Moore Coulomb model, and the results for the parallel I1 model are being presented in a separate venue, almost concurrently with this conference. This slide shows a comparison between the calculated and recorded acceleration time histories. The time histories corresponding to the left crest instrument are compared in three directions in this frame: the upstream downstream direction, the cross canyon direction, i.e. parallel to the axis, and the vertical direction. A similar comparison is made for the right crest instrument in this frame on the right. It may be seen that the calculated motions, which are shown in red, approximately resemble the recorded motions, which are shown in blue. And this is in spite of the crude nature of the Moore Coulomb model. Beauty, however, as they say, is in the eye of the beholder. A comparison of the measured, of the crest displacements is shown in this frame, where we compare the measured values are shown by these squares with the calculated values shown by the blue line. Also in the vertical direction and in the upstream downstream direction. The comparison indicates that the calculated crest settlements agree reasonably well with the measured settlements. The model, however, overpredicts the transverse horizontal displacements. However, it captures the sense of the displacements and also the sense of rotation of the crest. The displacements at the crest in the cross canyon direction were not measured. However, the analyses indicate that the left side of the crest moved towards the right, that is towards the center of the dam, while the right side moved towards the left. This can be seen more easily by examining the pattern of surface horizontal displacements resulting from the model. That pattern indicates that portions of the dam crest near the abutments moved towards the center of the dam, while at the same time, the slopes spread upstream and downstream. The corresponding permanent volumetric strains calculated from the analyses are shown in this slide. And volumetric strain is used as a proxy for tensile strain, simply because it is a good indicator of net tension under conditions of combined tensile stress and, tensile in shear and compressive strain. The frame on the left shows a plan view of the calculated surface volumetric strains, while the frame on the right shows section views for the maximum longitudinal section and the right crest section. The amplitude of the calculated strains is shown with this colored scheme, in which strains increase with the lighter, brighter colors. It may be seen that the pattern in location of tensile strains at the surface, which actually have approached about 1% or so, agrees reasonably well with the observed pattern of cracking at the dam. And the locations of the largest cracks agree with the largest calculated strains. It is also interesting to note that the analysis is capable of reproducing the depth of tension that corresponds to the depth of cracking that was observed after the earthquake. So these two case histories have illustrated some of the key aspects of Embankment Dam cracking under earthquake shaking. I would like to summarize those for you in closing, and also leave you with the following thoughts. First, earthquake-induced cracking commonly represents a potential failure mode for embankment dams because it can lead to dam breaching. Cracks oriented transverse to the dam axis and that allow concentrated flows through the embankment are particularly dangerous. Cracks from earthquakes are frequently similar in pattern to cracks caused by static loads and are typically near vertical, although due to arching, they can also take non-vertical orientations. But this is actually an very important observation, because if one wants to assess potential zones where earthquake cracking might be expected, it is important to study the pattern of cracking under static loading of a dam. Moderate deformations during construction in reservoir loading can lead to cracking of stiff cohesive materials, and in the absence of reliable filters, to internal erosion of an embankment dam. Steep abutment slopes and foundation shape in stiffness discontinuities can lead to differential settlements and cracking of stiff cohesive materials to depths greater than 30 meters. Earthquake shaking can disturb metastable stanched piping conditions and reactivate internal erosion. The evaluation of potential dam failure due to earthquake cracking requires reliable assessment of the location and extent of cracking. Cracks can be expected where and when tensile stresses exceed the tensile strength of cohesive soils. Coarse, cohesionless soils are unable to support open cracks. However, and this is important, due to apparent cohesion, partially saturated fine to medium cohesionless soils can temporarily support open cracks and hold a roof. Three-dimensional nonlinear dynamic analysis methods can be useful tools for evaluating earthquake-induced cracking of embankment dams. Earthquake shaking in the dam longitudinal direction plays a key role in the development of transverse cracking in embankment dams. And finally, reliable filters and drains are essential to reduce the risk of leakage and internal erosion associated with potential cracking of embankment dams. In this regard, it is very relevant to examine the wisdom and foresights of Professor Peck. As he stated in 1980, the literature already has much to say about cracking of earth dams. The emphasis, however, is on the mechanics of producing the initial cracks, an aspect that has recently become at least partially amenable to analysis. The analytical results serve a useful purpose. Reduction of cracking can undoubtedly be achieved most successfully if the causes of cracking are understood and avoided. Nevertheless, to accord with the principle of defense in depth, every dam should be designed on the assumption that the core may crack and that the dam should be safe even if it does. Thank you very much. I can see Brad, but
and I think we're back on here.
I'm not
thank you,
sure if I'm
Lelio.
supposed to take questions or not. In any case, I want to thank everyone that listened to the presentation for their attention.
Thank you, Lelio. I think one of my favorite things about our award lectures is that they're named for people and they're given in the spirit of these individuals who so many of us have had personal connections with. A lot of disciplines don't have that. You don't see any mathematicians who lived in the time of Archimedes, for instance, because that was 2,000 years ago. So normally what would happen for those of you watching is that right now, Lelio would have the Peck medal awarded to him, or that would have happened before the lecture, and handshakes and photos with the Geo-Institute president. It's a little different this time. We sent Lelio the medal in the mail, and it made it there in one piece. We do know that. But I just want to say thank you again. And another thing I really enjoy are the reflections on the words of these greats of this field and the expression of how research has grown and sprouted out of the seminal work that they did, which wasn't too long ago, actually. So this was fantastic. I think we'll do a little wrap up here. For those of you who are in person, it's time to get out and recept, I think, outside with the exhibitors. For everyone, we'll be back at it tomorrow. The opening session begins at 8:30 with a presentation by each of the four partner organization presidents. So you'll want to be there for that. At 11 o'clock will be the Smith lecture tomorrow morning, and we'll be right here on YouTube with that as well. And tomorrow afternoon, well, still the morning at 11:15 a.m., all these times are central, the Osterberg lecture. And tomorrow afternoon, I'm looking over my schedule here so I don't mess up the times, at 4 o'clock will be the O'Neill lecture. All of these are excellent. They will all be live streamed. You will be able to see them right in this very room if you are at the conference in person. And we hope to see you back for those. Everybody have a good night and enjoy the week at IFCEE.